So we've been talking about motion and motions in the sky and how all the sky shifts and things change. That's the power of that Stellarium software, is it shows you what the sky looks like from anywhere on Earth, any time of day, any day of the year, because it keeps changing on us. So we've talked about diurnal motion, and diurnal motion is this daily rising and setting. We've talked about annual motion. Annual motion is due to the motion of Earth around the sun. And so that gives rise to the 4 minutes a day shift that exists in the sky. Now, you combine the diurnal motion, the annual motion, and that relates to how we keep track of time on Earth. And annual motion gives rise to the seasons because of the tilt of the Earth. And so all of that is keyed in there. And so that actually describes most of the kind of motion that you see. Well, one of the other things that happens is precession. It's a 26,000 year cycle. And so over 26,000 years, you have this gradual shift in the sky, and all the coordinates are shifting a little bit. Stellarium keeps track of that. And that's because Earth changes the direction it's pointing. It changes where the North Star is going to be. And then we have nutation. That's this wobble in the inclination or the tilt of Earth. And that changes the tropics. It also changes the coordinates a little bit. And so, so these are all motions. But for all of these, it's still Earth that's moving. Sky is not changing. Earth is moving, and so our view of the sky is moving. So the question is, do the stars themselves move? Claudius Ptolemaeus, or we call him Ptolemy, was an ancient astronomer, and he lived in Alexandria in Egypt, and he recorded positions of stars with unparalleled accuracy. And he published this giant work called the Almagest, which was the sum knowledge of everything that was known, and was the most precise record that had existed at the time. And it was really big on some of these stars. Some of the stars, for example, Sirius was very important to the Egyptians. They would keep track of when Sirius rises and sets. Remember, things rise 4 minutes earlier every day. And so Sirius would rise 4 minutes earlier every day, and so they'd keep track of exactly when it was rising with the sun. We called that the heliacal rising. And so when they did that, they noticed that it was 365 days or 366 days, but it was a little bit more than 365 between when it happened. And so they started building a calendar that was 365 days long. And then every 4 days, every 4 years or so, they'd toss an extra day in to match it up because it wasn't exactly 365. So that was the beginnings of the 365-day calendar with a leap year. Arcturus and Aldebaran were likewise very important things. And so they monitored these stars very, very, very carefully. And yet Edmund Halley, British astronomer, in the 18th century, measured positions that were about a degree from where Ptolemy had them. Now that was kind of a big deal, because a degree is like twice the width of the full moon. That was a huge error for Ptolemy, particularly for stars that were culturally and so forth as significant as those three. And so Edmund Halley suggested maybe stars actually do move against the background sky. They just do so very, very slowly. And so that we call proper motion. Well, it took many years before proper motion was eventually discovered. And there were several stars that were found to have some proper motion. Kruger 60, several others. The star that currently has the record holder as the most proper motion was discovered by American astronomer Edward Barnard, and so we call it Barnard's star. And so you can see here in this photograph, these two photographs here, that there's this star there and over here, and a little bit an arrow points to a little star. I don't know why every astronomy lecture has to have eventually a picture of stars with an arrow pointing to one of them. But here it's pointing to this little dot right there. Well, that dot isn't there in this picture. That dot is up there between. It's between this star and that star. And so that dot moved a little bit between the two pictures. The two pictures were taken here almost 20 years apart. And so the star moved a little bit. And so that star we call Barnard star. Now technically it is BD plus 4 degrees 3561A. There's actually a 3561A and a 3561B because there were two stars right next to each other that Dreyer saw, and he called them 1A, 1B. It currently has the record as the most proper motion of any star, and that is a little over 10 arc seconds per year. So now that means you got to go like a long time, like 150 years, until it moves the width of the full moon in the sky. And this is a very, very dim little star. It's not even visible to the naked eye, but it is the record holder for the highest proper motion star in the sky. Okay, and here's a series of pictures that were taken with the same telescope, slightly different exposures, which is why the background stars, the dim ones, can come and go, and that shows Barnard star moving across the sky. It's not the only one moving. Sirius moves also, and Sirius is right now down to the left of Orion, but in the distant past, Sirius was way up in the northern part of the sky, very far north. Would have been very impressive because it would have been almost like a North Star at the time if you were to go back millions of years. Okay, it's now moving so that in another few tens of thousands of years, maybe 75,000 years or so, it's going to be so far south it's not going to be visible from Texas anymore. It's also getting brighter because it's getting closer. So as these stars are moving, they're also not just moving side to side, but they're moving towards us or away from us. So it's actually going to be even brighter in the future. Well, to figure that out, we need to be able to measure distances. And that's going to be our next topic, is how do you actually measure the stars, measure the distance, make these measurements as to what really is going on with them. So right now we're just doing background material. Okay. And this is an interesting little slide right here that shows the stars of the Big Dipper, okay, and moving into the future, and you see that these stars have some proper motion, and so it's not always going to be dipper shaped. And so this is an example of proper motion right there. I think that's kind of an interesting little graphic right there, showing how the stars are moving across the sky. But as I said, our next topic is to actually find distances of stars.